Okay, so this is a new section, and this is finishing sort of section 1.5 and beginning 1.8, and I'm going to stop with you all where I stopped with my 9 o'clock class, so on Friday we'll all be on the same page. So a function y, and if you want you can pause this and fill this in first, and because we're going to do an example, and I'm going to fill in some of the things just to save time for this video. Alright, so for even and odd functions, we'll be talking about this some more, and so I just want to give you a definition of what an even and odd function is. So again, remember that y equals f of x. We already talked about that. And it's even if for each x in the domain, f of negative x equals f of x. So for example 1, let h of x equal x squared plus 1. Alright, so if this function is even, first we need to evaluate it. To find out if it's even, I should say, we need to evaluate h of negative x. So again, remember with the function, it's a machine. For every input you get an output. What this function does, whatever input you put in this case it's going to be negative x, this function squares that input and adds 1. So it's going to be very important to use parentheses for this function when you have negatives in general. You want to use parentheses, and if you want to just use it in general, you can. So negative x squared is going to give us x squared plus 1, and that equals h of x. Okay, so in this example, we would say h is an even function. Or you can just say even. And I'm going to use abbreviation fxn to represent function. Okay. Now again, you can stop this and write out what an odd function is before we do the example. But a function y equals f of x is odd if for each x in the domain, f of negative x equals negative f of x. So notice the difference in these two functions. This is the input. You're inputting negative x. Here you're taking negative of the entire function. So basically you're changing the signs of that function. Alright, so again, let's look at an example. So this time let g of x equals x cubed. I'll keep it simple. Then now we have to find what g of negative x is. And so that's going to be negative x cubed. And so that's a negative x times a negative x times a negative x, which equals a negative x cubed. And then if we evaluate negative g of x, this is going to be negative times our function x cubed, which gives us a negative x cubed. Okay, so over here, so g of negative x equals negative g of x, thus g is odd. Okay, so now we are moving on to section 1.8, which are composite functions. But before we talk about composite functions, we're going to talk about some other new functions. So often we build new functions out of existing functions. So let's say we have two functions, f and g. From this, we can define 4 new functions. All right, and I wrote them below. So f plus g, f minus g, f times g, and f divided by g. Okay, and so note the domains of these new functions are the intersections of the domains of f and g. So however, for f divided by g, so remember again, in terms of domains, our restrictions, or what we look for now, are if it contains a denominator or even root. And so f divided by g, we're going to have to throw out all those inputs, or find all those inputs that make g of x equal 0, because those inputs will not be in our domain because it's in the denominator. Okay, and this is sort of how they work. So you could see, I want to show you both ways it can be represented. So f plus g of x, that's the same thing as writing f of x plus g of x. You can see it both ways, so I want you to get used to seeing it both ways. F minus g of x, that's the same as f of x minus g of x. F times g of x, that's equal to f of x times g of x. And f divided by g of x is equal to f of x divided by g of x. And again, remember, for this function in terms of domains, you need to find out where that g of x equals 0, because those values will not be in your domain. Okay, so we're just going to do some examples of these functions, and for f of x is equal to negative 9x plus 4, g of x is equal to 3x minus 7, and we need to find the following and the domain. So I sort of started setting up the A. We have f plus g of x, which we know that's the same thing as saying f of x plus g of x. And so that's equal to, and I use parentheses. In this case, you don't have to, but just to get in the habit, because in certain cases it is necessary to use parentheses. So the first term, that's our f of x, that's our g of x. And now, so this becomes negative 9x plus 4 plus 3x minus 7, because we can take it out the parentheses. And you can see we have some like terms going on. So we have the two x's are the same, and then we have our constants. So our final answer will be negative 6x minus 3. And in terms of our domain, again, remember, we've already talked about this is a polynomial function, so the domain of any polynomial function will be all reals. Okay, so what you can do actually now is stop the recording here. Try B, C, and D on your own, because on the next page I'm just writing the solutions. And if you have any questions about those solutions, you can ask me in class on Friday. Okay, so here are your solutions for B, C, and D. Make sure you check your answers. And again, if you have any questions, you can ask me about them on Friday. Alright, so now we're going to get into some fun stuff with the compositions of two functions. Alright, so first let's draw a couple diagrams. So we're going to have a function, you know, it's a machine, so we have this machine, and we're going to input x, and the name of our function is f, so our output will be f of x. And then we're going to have another function, g, and when we input x into g, we get out g of x. Very good. Okay. So now, what if we combine these functions? Okay, so combining f and g. Alright, let me use another color. So this time, when we combine, we still start off with x, and we put that into our f function, and we get out f of x. But now, we're going to put in f of x into our g function and get out g of f of x. Okay, and that's the notation for a composite function, g of x of x. And there's also another notation, but that's sort of the idea behind what a composite function is. It's two functions that we're combining. We're composing together. So this machine combining the two functions, this is called the composition of g with f. Okay, and it's denoted two different kinds of ways. You can denote it as g circle f, so that circle means composite, or g of f of x. Okay, and what this tells you, you see how the functions are, f is sort of nested in g. This function gets applied first. Okay. Okay, so warning. Before we move on to do an example of a composite function, I wanted to give you this warning. f of g of x is not equal to g of f of x. We'll see that with our next example. Okay, so in other words, composite functions are not commutative. All right, so f of g of x does not equal g of f of x. And another warning is f times g of x is not the same as f of g of x. All right, so you want to be careful because this is sort of a common mistake students make. This first one, if you remember, this is multiplication. You just multiply the two functions together. The second one is a composition, and we'll do our next example. We'll talk about that. So that's a composition. So note, this is multiplication of functions, and this is composition of functions. Okay, so example 2 is going to be our last example because this is where I stop with my other section. So after that we do this example, you all will be caught up with the other section. Remember, so now we have two functions. F of x is the square root of x plus 3 and g of x is x squared. So you need to find f of g of x and g composite f of x. Remember, this is the same thing as g of f of x, just like this is the same thing as f of g of x. So you can see the notation either ways. I just wanted to show you the different ways of the notation. So we're going to do f of g of x together, and then you're going to do g of f of x on your own, and we're going to go over the solution in class on Friday. Okay, so again, remember, this is a composite, so this is f of g of x. You always start from the inside out, so you could have a composite of a composite of different functions. You always just start from the inward and work yourself out. All right, so for f of g of x, this is going to equal f g of x. You substitute in what g of x equals. So g of x in this example is x squared. And so now we have f of x squared. So now we have to put this input into our f function. And that's going to equal 2, or the square root of our input is x squared plus 3. And you can't do anything else with this function. You cannot break up the roots because addition doesn't, you can't break up roots with addition. And so that would be your final answer. The only other way you could write this, and this is something to keep in mind for the future, is that x squared, you can write as x squared plus 3 to the 1/2. That's another way to write that problem. And in general, so you should make a note of this because this rule, in case you forget, will definitely come in handy. The n root of x always equals x to the 1/n. Okay, so just keep that rule in mind. And now I want you to do g of f of x on your own. Okay, and I will stop here.